Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solve the problem number 14. Let's consider this network consisting of 4 resistors labeled R1 through R4 as well as 2 independent voltage sources V1 and V2 and 1 independent current source IS. The question now is to calculate the value of Ix using Thevenin's theorem. Ix is the current through the resistor R2. Let's move on to the solution. By applying the Thevenin's theorem between terminals A and B, we can replace this circuit with a voltage source in series with the resistor, which will be denoted as VTH and RTH. In our example, RTH is connected in series with the R2, which will plays the role of the load. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuits, which means the voltage source will be replaced by a short circuit and the current source will be replaced by an open circuit. The Thevenin's resistance represents the equivalent resistance between terminals A and B when R2 is disconnected. That means RTH is equal to the series combination of R3 and R4 connected in parallel with the R1. Therefore, RTH can be calculated using the following formula: R3 plus R4 times R1 over R3 plus R4 plus R1. And if we replace the resistors with their numerical values, we obtain RTH is equal to 3 ohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage calculated between terminals A and B when R2 is disconnected. To find the open circuit voltage VOC, I'm going to apply the nodal analysis method. And I will consider I1 is the current through the resistor R1, and I2 is the current through the resistor R3, and I3 is the current through the resistor R4. By applying Kirchhoff's current law at node A, we can write I1 minus I2 is equal to 0. The current flows in this direction is equal to 0 because we have an open circuit. Now, by applying Kirchhoff's current law at node N, we can write IS plus I2 plus I3 is equal to 0. And according to Ohm's law, I1 is equal to V1 minus VA over R1. And I2 is equal to VA minus VN over R3. And I3 is equal to V1 minus V2 minus Vn over R4, where Va and Vn present the node voltages respectively to node A and node N. Now, by substituting A and B in 1, we can write V1 minus Va over R1 minus Va minus Vn over R3 is equal to 0. If we replace the voltage and the resistors with their numerical values and we continue simplifying this equation, we obtain 14 plus Vn minus 2 times Va is equal to 0. Now, by substituting B and C in 2, we can write 3 plus Va minus Vn over R3 plus V1 minus V2 minus Vn over R4 is equal to 0. And if we replace the voltages and the resistors with their numerical values and we continue simplifying this equation, we obtain 32 plus 2 times VA minus 3 times Vn is equal to 0. Now by performing 4 plus 3 times 3, we derive one equation in terms of VA. That means VA is equal to 74 over 4 is equal to 18.5 volt. If we look here that VA is equal to VOC, that means VTH is equal to VA is equal to 18.5 volt. Now the current IX from here is equal to VTH over R2 plus RTH. And if we replace VTH, R2 and RTH with their numerical values, we obtain IX is equal to 3.08 amps. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in the SPICE simulator. This is the original circuit, and this is the Thevenin's equivalent circuit. I connect here an ampere meter in order to measure the current IX through the resistor R2 in the original circuit, and I connect also here an ampere meter in order to measure the current IX through the resistor R2 in the Thevenin's equivalent circuit. Let's move on to analysis. DC analysis, calculate nodal voltage. We can see here that the current IX through the resistor R2 is equal to 3.08 amps in the original circuit and is equal to 3.08 in the Thevenin's equivalent circuit. From the simulation, it becomes clear that the current IX is similar when using both the original circuit and the Thevenin's equivalent. This similarity validates the correctness of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Thevenin's theorem. Take care and bye bye.